Everyone's here. Everyone's happy. It's week 4, which means, I guess, what does that mean? The Super Bowl's this week. Everyone's excited about that? Good. Let's see. So what have we got today? I am planning to talk just a little bit more about some of the stuff from Chapter 5 we talked about last week. I want to just make sure everybody's on the same page when it comes to counting. And we left off, I think, with an example where I asked you guys about the probability of sharing birthdays and that sort of thing. And I think we did talk a little bit about Bayes' theorem last week as well. I know there's some questions from the homework, so I want to make sure that we get to those. And then we will talk about some of the Chapter 6 material when we get into discrete random variables. So we'll talk about the binomial, talk about the Poisson, and the hypergeometric, and hopefully help us understand what's going on with those things. So before I jump into the counting, just so I have a good idea of how many questions people have from the homework. So from homework 3, which is on Chapter 5, are there questions you guys want to see?
From the first one, number 12, and 3 questions.
I'm sorry.
3 questions.
3 questions from number 12?
Or no, from the whole homework.
Okay, so 12 is the first one?
Well, I just got number 1, but I don't know how I got it.
Okay. So we're going to look at number 1, what other one?
12.
12 and...
And trying to find
15, okay. So this is the homework that's due on Thursday night, and the quiz number 3 is due on Friday night, which corresponds to this stuff. So this will be a good opportunity to ask questions and see how to do these things. So we'll look at those, and in fact, maybe we should, let's see, does one of those have to do with Bayes' theorem? The biometric security system. Okay, so let me talk a little bit about Bayes' theorem. Let me talk about the counting, and then when we get to Bayes' theorem, we'll go and look at these questions. Okay, so I think last time I mentioned something about the multiplication rule for counting, which says if you have multiple sub-processes in a process and you want to know the total number of ways that you can complete the process, all you have to do is count the number of ways that you can do each of the sub-processes and multiply those out. And so that becomes relevant to us when we ask questions like, what's the probability that at least 2 people have the same birthday? So we went over this last time, and I showed you a website that there's a link in the week 3 folder for that will allow you to just pick different numbers of people. So if we have a room full of 40 people, you can say, what's the probability at least 2 of us have the same birthday? And we actually asked everybody, and somebody made a bet, didn't they? Who was it that made the bet? Somebody bet me. Was it you?
I was one of them.
You were one of them? Okay. So you're getting an F in the class? Yeah, okay. You can still come, though. That's okay. And I guess the other people just decided not to come. That's okay. So how do we calculate the probability for something like that? Well, it's actually not that difficult if you think about it in the right way. And so we could say, first of all, what if we had just 2 people in the room? What's the probability that out of 365 days of the year, 2 people are born on the same day of the year? You'd say, well, the first person can be born on any number of those days. And it doesn't matter what day the first person is born on. The probability of the second person's also born on that day is 1 divided by 365. And so we're ignoring leap year here. Okay, so if we have at least 2 people with the same birthday, what does that mean? That means in a group of 40, we could say there's 40 people how many ways can we have two people chosen out of 40? How many pairs are there if we have 40 people? What do you think about that question? So we said probability any 2 people have the same birthday is very small, 1 out of 365. But then we're going to say, yeah, but if we have 40 people, how many pairs are there? Okay, so this, I think I mentioned last week about combinations, where we said if we divide the group up into 2 groups, all right, so say we've got 40 people here, and I want to choose 2 of them, I could say here's the 2 that I'm going to choose. And really what I'm doing is saying I'm putting the group into 2. I'm splitting the group into 2. The 2 that are the pair that I'm interested in, and then the 38 that are I don't really care about. Not that I don't care about them, but I don't care about them. So I would say, how many ways can I order all of the people, or all of the objects, if you don't think about it more generally. So there's 40 ways I can choose the first one, 39 ways I can choose the second one, 38 ways I can choose the third one, 37, 36, 35, and so forth, all the way till I get down to the last person. There's only one way in which I can choose them. So imagine I've got 40 people in the room. I'm going to say, okay, here's on these first 3 rows, there's 40 seats. I'm going to put everybody in order, and I'm going to do it randomly. So for the first seat right here, I've got 40 people I can choose. Once that person has a seat, now I've got 39, and then 38, and so forth. When I'm doing combinations, I don't really care about the order in which I am selecting these 2 people. So if I said, here's a divider right here, I'm going to put everybody in order in these first 3 rows or 4 rows, however many it takes, but I really only care about the 2 people that are in these first 2 chairs. Then I would say I have 40 factorial ways in which I can arrange all of the people in the class. All right, so that's 40 factorial, but I don't care about the ordering of either of the groups. I just want to know how many ways can I pick 2 people and sit them right there. So I can rearrange these 2 people in 2 factorial ways, and I have the same pair, but I can also rearrange these 38 people in 38 factorial ways. In other words, all I'm doing is saying, I don't care what order is, I want to know how many ways I can have 2 people selected. So I get 40 factorial divided by 2 factorial divided by 38 factorial. That's the number of pairs in the class. So out of 40 people, I get 40 choose 2 pairs. Okay, so that's one way to think of this. What does 40 choose 2? Well, it's just this number here. Let me pull up Excel because you can do this with your calculator if you like, but these numbers are going to get big. Okay, so in Excel, I can get this number here by using the function combine, C-O-M-B-I-N. It stands for combinations. So if I want to take so combin 40 comma let's start at 2. Actually, let's start at B2. All right, and I'm going to put 2 in here. Sorry. All right, B1, that's what I want. Okay, so if I have 40 people, turns out there's 780 pairs of people. So if you're saying each pair has a very small probability of having the same birthday, well, that's consistent with there being a high probability that at least 2 people have the same birthday because there's so darn many pairs. There's 780 pairs of people. Okay, so this is one way you can start to think about this. This number actually turns out to be n times n minus 1 divided by 2. And do you guys know who Gauss is? Did you ever hear the story about when Gauss, he's a famous mathematician, he was in elementary school in Germany somewhere in the 1800s, and he was really bored because, you know, he was one of these genius kids, and so he's rambunctious, and one day he got into trouble, and his teacher said, hey, no recess for you. Everybody else is going to go out to recess, and you're going to sit at your desk, and you're going to add up the numbers from 1 to 1,000. And when you get that done, then you can go out to recess with everybody else. And Gauss said, oh, okay. About 15 seconds later, he handed the correct answer to the teacher and said, here's the sum. And he went out and played. And so how did he do that? Well, it's actually very similar to this thing right here. He said, and I'm going to do it with 1 to 100 instead of 1 to 1,000. He said, okay, here's 1 plus 2 plus 3 plus 98 plus 99 plus 100. So if you had to add up all these numbers, how would you do it? Brute force, or the plug and chug, or the crank, whatever they call that, would just say, just add them up. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, and so forth. But that takes a while, especially if you're going up to some big number like 1,000. So what did Gauss do? He said, well, if I take this first number, 1, and I add it to the last number of 100, what do I get? 101. And if I take the second number, 2, and I add that to the second to last number, 99, what do I get? 101 again. And then if I take 3 and I add that to 98, what do I get? 101. So how many times do I have to do that? So I'm going to go 1 plus 100, 2 plus 99, 3 plus 98, 4 plus 97, and so forth. I'm going to do that 50 times. So I have 50 times 51 over 2. Sorry. 50 times. It's 100 times 101 divided by 2. So this is 50 times 101, which is 50, 50. So if I'm adding up the numbers from 1 to 100, the answer is 5,050. If I'm adding up from 1 to 1,000, the answer is, just throw another 0 on that actually. Yeah.
Why is it 101 and not 99? Are you following like the formula from up there, or is that like?
So this formula is similar. It's actually a little bit different. This one is n times n plus 1 over 2. But if you're talking about pairs, what you're saying is instead of having n plus 1, you're going to have n minus 1. So This right here would be as if you were, so imagine that you went to a party and we said, okay, everybody's going to shake everybody else's hand. You say, how many handshakes are there? Well, that's the same as counting the number of pairs of people. And that's going to be this one here, n times n minus 1 over 2. But if you said, oh, how many, if you shake your own hand, then it's going to be this number here, n times n plus 1 over 2. Okay, so it's really just the way you're thinking about, am I adding up 1 plus n, 1 to n or 1 to n minus 1. And if you're talking about pairs, you're really adding up n1 to n minus 1, which means you could write this as n minus 1 times n divided by 2 if you wanted. Okay, so this is pretty interesting. These the number of pairs grows very, very quickly, and if we're talking about the probability of at least 2 people having the same birthday, that means we got the probability of exactly 2 shared birthdays, but that's not the only way this can happen. I don't remember in this class if we had multiple shared birthdays, but it's possible that if at least 2 people have the same birthday, that means 2 people have the same birthday and 2 other people have the same birthday, but it's different than the first 2, and maybe even other people. There's other pairs. There's lots of different ways this can happen. It's also possible that we could have 3 people with the same birthday, right? If at least 2 people have the same birthday, then that means 3 or 4 or 5, and so we'd say the probability of at least 2 people having the same birthday plus probability, not at least exactly 3 shared birthdays. But it's also possible to have 2 birthdays, or 2 people share a birthday, and then 3 people share a different birthday. All right, so this gets to be very, very complicated very quickly. But what happens if we're talking about the number of, you might say, triplets? If I have 40 and I'm going to choose 3 people, how many ways can that happen? Well, this is just going to be 40 factorial divided by 3 factorial divided by 37 factorial. And let's come over here and paste that in. And I'm going to put a 3 right there. So the number of triples are 9,880 out of 40 people. It's combine, C-O-M-B-I-N, or combin, stands for combinations. And I'll post this on Blackboard. Okay, what if I'm choosing 4 people? Or 5, or 6, or 7, or 8, or 9, or 10. And let's see, let's just I want this down to 20, and then let's copy and paste. So what happens as the number of people I choose goes up? How many ways can I get 14 people out of 40? Well, it's 2.3 times 10 to the 10. So that's 2 billion. Where does this max out? It maxes out right here at 20. So 40 choose 20 is 1.38 times 10 to the 11. That's a very big number. So what I'm saying is, if I took 40 people in this class and I said, I want to choose 20 of you guys, and I'm going to do it at random, there's over 13 billion ways that can happen, which is pretty big. If we sat around and did all that, it would take us a long time to do that. Okay, so that's not exactly what's going on here. I'm just writing these things out to show you that this probability gets to be very complex. But it turns out there's an easy way to find this probability, and that's to use the the law of complements. And the law of complements says if I have some event that I'm interested in and I want to know the probability of it, I can find that probability by subtracting the probability of the complement from 1. So in other words, if I said 1 minus the probability of what? If at least 2 people have the same birthday, the complement of that means that nobody has the same birthday. Okay, so I'm going to take 1 minus the probability of no shared birthdays. And that actually is kind of the reason why this question is asked the way it is. At least 2 people having the same birthday. That covers everything that's not a unique birthday setup. So 1 minus the probability of no shared birthdays. Well, I can calculate that because if the first person is born on whatever day they're born on, doesn't matter, I can then say what's the probability the second person's not born on that day. In other words, how many days can the first person be born on, if I'm talking about 40 people, such that they don't have a birthday with anyone else? Well, we're talking about the first person, so there's 365 different days that they can be born on. And then I would say, what about the second person? How many days can they be born on such that they don't share a birthday with the first person? You'll say 364. And then 363. All the way down until we get to 365 minus 40 plus 1. Okay, that's the number of days, or the number of ways that we can have unique birthdays for 40 people. And in order to get a probability, we have to divide that by the number of ways in which we can have birthdays without restriction. So we have 365, 365, 365, right? If there's no restriction, that's what's going in the denominator. And so this is 1 minus 365 factorial divided by 365 minus 40 factorial, all of that divided by 365 raised to the 40th power. And so this probability is the probability that I'm interested in. Now, it turns out that the numerator here, the 365 factorial divided by 365 minus 40 factorial is the number of permutations of 365 objects taken 40 at a time. And I think I talked about permutations in the video, so hopefully you've seen those, but permutations are just like combinations. Combinations say n choose r. Right, if I have n objects and I want to choose r of those, that's going to be n factorial divided by r factorial divided by n minus r factorial. This is just what we looked at right here. Number of ways that we can choose 2 out of 40. But this says order doesn't matter. Right? Permutations are a little bit different, because with permutations what we're saying is when we divide our population into groups, 2 groups, we do care about the order of one of the groups. So if we have, we'll write it like this, P n r, this says n factorial divided by n minus r factorial. In other words, I would say, say n is 5, I would say I've got 5, 4, 3, 2, 1. So 5 factorial ways that I can arrange these 5 objects, and I do care about the order of the first 3. So I'm only going to divide by the order of the last 2 that I don't select. Right? In other words, if I have A, B, C, D, and E, and I select A, B, C, D, and E, sorry, A, B, and C, that's going to be the same as taking A, B, C, and E, and then D, right? Because all I care about are the first three. But that's different than BAC or ACB or CAB or whatever else. Okay, so that's the idea behind permutations, and you can use that to answer this question: what's the probability at least two people have the same birthday? And so if you come over here to Excel, let's just plug it in. So this is probability. Birthdays. This is going to be equal to 1 minus permutation, so PERMUT, that's the function built into Excel. There is a permutation and a combination on most of your calculators if you have like the TI-80 variety, but we're going to say we have 40 and we're going to choose E2. And then we're going to divide that by sorry, I messed that up. Permutation 365, comma, we'll put E2 in there, and then I'll put E2 in just a minute. But we're going to divide all that by 365 raised to the E2 power. Okay, so what's E2? We're going to put 40 in there. And we see that when there's 40 people, there's almost a 90% chance that at least two people have the same birthday. So what's going on is that this this ratio right here gets very small very quickly. And you could play around with this and just say, well, what about 23? If 23 is the number, then the probability is about 51%. So the next time you go out to a party with your friends, say, hey, let's make a bet. There's 50 people here. What do you think the probability is at least two of us have the same birthday? And most people say, oh, it's really low. But then you say, oh, hold on. Put 50 in, and you see it's 97%. So don't tell them the probability until after they bet you, of course. That way you can make some money. What happens if you have 100 people? Essentially 100%, at least to 12 decimal places. So that's pretty cool. You can go and look at that. Other things that you can do with these counting methods. Well, so I grew up out west, the United States, and I've got a wife and 4 kids, and a lot of family members still live out in the west, and you know, it's expensive to fly out there. So so what do? Every summer we drive, and it's about 3 days in the car, and so it's sometimes hard to keep kids occupied and keep them from fighting and whatever else. Imagine riding for 3 days each way. So there's some games that we like to play, and some of these games can take a long time. One of them's called, this is like one of my favorite games of all time, Guess the Secret Serial Number. Okay, so you got a captive audience. You need a captive audience for this. You're driving across the country for 3 days, and you say, okay, I'm thinking of a 6-digit number. And go ahead, guess. As soon as somebody gets it, it's like, it's the most amazing thing. It's just like an eruption in the car, just pure euphoria. Everyone's just, yes, someone got it. It's awesome. So who wants to play? 6 digits. Go ahead. Nope, that's not it. Okay, that's one guess.
0, 0, 0, 0, 0, 0.
No. Yeah, go ahead. Yeah, you were. Yeah, go ahead.
2, 3, 4, 5.
No, that's not it. No, that's not it.
0, 1, 3, 0, 18.
Oh, that's not it. Anybody else? Yeah, in the back. Yeah, go ahead. Yeah, you were. You were going like that. That counts. Go ahead. Come on, just give us a 6-digit number. Spit it out. Nope, that's not as good. Good, really good guess though.
687530.
No.
264969.
No. Was that the serial number off your wrapper there? No, that's not it. Okay, well this is. I mean, you keep playing, and maybe you do have to be in a car driving across the country for hours and hours and hours in order for it to be really fun. But do you think I could induce you guys somehow to play this game, like not when you're driving across the country and not when you're sitting in class and you go to scratch your nose and I make you say something? There's nothing I could do to. I mean, there's got to be the right incentive structure that would make you want to play this game, isn't there? Isn't there? What's the incentive structure we need? No midterm. Well, if you get, yeah, maybe if you guess it right, then you get 100% on the midterm. Do something like that. Money works, okay. So how would it work if we were to involve money with this? If you get it right, you get a bunch of money? Okay, so have you heard of that before? What's that? In fact, this game is extremely popular. People line up at gas stations and all sorts of different places to play this game, and they pay how much to do it? $2 a guess. Yeah. Pretty crazy if you think about it in that way, right? So what do they say? It's actually more than a 6-digit number. Could be up to a 12-digit number, but they say this last number's got to be something between 1 and 39. And then these other 5 have to be, I don't know what the exact numbers are right now, but for Powerball anyway, they keep changing these things. So we'll just say you have to pick 5 numbers between 1 and 59, and then you have to pick another number between 1 and 39. So you put these in order, so you'd have like 6, 18, 29, 32, and 50 maybe. That would be a guess. And then the last one, 1 to 39, let's just say 31. So what's the probability you're going to get this right if you do it this way, just on a single guess? The 6-digit number that we were playing in the car, that's a little bit easier. It's just, 10 to the 6, that's like 100,000. Is that right? Yeah. So what's the probability you're going to get this right by guessing? Well, so let's make sure we understand what's going on. We have 59 numbers to choose from. And we can choose 59 for the first one. And there's not going to be repeats here. So 58, 57, 56, and then 55. And now we have to ask the question, does order matter here? Do you have to get them in the right order when you play the lottery? Do you? So Powerball, when they draw them out, they put them in order for you. So you don't actually have to get the order correct. Nope, you don't. It would make the problem much difficult, 120 times more difficult if you had to pick. So in other words, what I'm saying is if you picked a 6 and then an 18, a 29, 32, and 50, and you said that's the order in which they're going to come out of the bin, the little ping pong balls, then that's a lot harder than saying, well, if 18 comes out first, then you're out of luck. If it's 18 and then 29 and then 6 and then 50 and then 32, that's more difficult than if you just say, well, it's any combination of, or any ordering of those numbers. So what we're doing here is we're saying it doesn't matter the order, so I'm going to divide by 5. That's the number of ways that I can pick one of those 5 numbers, and then 4, and then 3, and then 2, and then 1. And this turns out to be 59, choose 5. Okay, so that's the number of ways that you can get to choose 5 of those numbers. All right, and then how many ways can you choose one of 39 numbers? Well, there's 39. 39, you can say it's 39, choose 1 if you want. So that's not equal to that, but so the number of ways that you can, or the number of tickets that are available. So this is lottery. We're going to say we have combin 59, 5 times combin 39, 1. So there's 195,249,054 possible tickets if they're using 59 and 39, which, like I said, those are numbers that are subject to change. They do look at how many people are winning the lottery or the jackpot, and how long they're, how big that's getting, and they change it over with time. In fact, it used to be like, I don't know, 15 years ago or so, they would say we want to keep the jackpot at about maximum $300-400 million, and so every time it would get up to be around there, there would be all sorts of hype, and the local news stations would call up and say, hey, we need a statistician to tell us, or a probabilist to tell us what the probability is that someone's going to win the lottery. And so they would call me up, and on TV they would ask me, what's the probability someone's going to win now that the jackpot's $400 million? And I'd say, well, the ticket says it right here on the ticket, 1 in $195 million. It doesn't change. And they're like, oh, that is so crazy. And they make this big deal about it, and the hype generates ticket sales, I guess. So more and more people buy it, and then the actual expected payout is going to be less if more people win. You have to split it up. So kind of some interesting things going on there. But what do they do now? Is $400 million big for the jackpot? I mean, if you're going to give me $400 million, sure, I wouldn't complain. But now they let it go as high as it can go. I think the biggest has been $1.4 billion. That was probably a year and a half ago. So, so what are the chances you're going to win? Well, it's 1 divided by that number if you buy a single ticket. How long should you expect to pay? A lot of you guys are business students. You're studying investments, that sort of thing. Is the lottery a good investment? What do you mean? I put $2 in and there's a chance I can get $1.4 billion out? I mean, it's got a positive expected return, but there's a giant risk, isn't there?
What about those people who play like the same numbers all the time, like different numbers?
There have been some successful lottery schemes where people have made money. Not in the Powerball, but there's other types of lotteries where a bunch of MIT students up in Boston would go out and buy $100,000 worth of lottery tickets, and they would hire undergrads and people off the street to just come in and fill out the lottery sheets, and then they would take them in and they process them, and there was kind of a flaw in the system I can't remember what that lottery was called. It's not the big one, but in certain circumstances, if there were enough tickets being purchased, the payouts would actually be pretty big, and so everybody thinks, oh, the lottery, I'm going to make lots of money off it, but the guys who did this for a few years before it was they changed the rules, they were working 80, 90 hours a week doing this stuff, and they could have gone somewhere else and probably made better money doing the same amount of work. So there's no really free lunches here. But if you are going to do this as an investment vehicle, and you'd said, what's the probability of winning then? Well, that's just going to be 1 divided by this number. So 5.12 times 10 to the minus 9. That's pretty small. If you were to take 10 tickets a week, so $20 a week, and you were going to do this for the rest of your life, how long would you have to live before you could reasonably expect to win? What do you think? Well, if you're taking 10 tickets a week, the probability you're going to win is, let's just kind of wave our hands and say you're 10 times more likely to win. And so if that's the case, then you would say the number of weeks that you have to wait that's going to be equal to this number divided by what? Just divided by 10, right? Because you're putting 10 tickets per week. So you should expect to wait for that many weeks. How many years is that? Well, it's going to be that number divided by 52. So 375,478.95 years. That's the reasonable expected, that's the expected waiting time for you to win. So $20 a week for that many weeks, how much are you going to end up spending? Sorry, $20 a week for this many weeks. You're going to end up spending twice what you're going to get back. Well, you're going to, not twice what you're going to, the lottery, the jackpot changes every week, of course, but you're going to spend almost $400 million over the course of 375,000 years, which is a good argument for what? Good argument for learning about math and learning that if you want to play games and it's entertaining and exciting, that sort of thing, that's maybe one reason to play the lottery, but it's not a good investment vehicle. It's really a tax against people that don't understand math. And so now that you've taken this class and you've seen this, you can make more informed decisions about whether you want to do that or not. Okay, so I told you we would talk about some of the homework problems. There's at least one on Bayes' theorem. So let's pull up the homework. Okay, so the first question was number 1. M&Ms are blended a ratio of 12%, 15%, blah, blah, blah. how many elements are there in the sample space? This is the question you had?
Yeah, I got all the answers except for the first one. Could not figure out the sample space, and then I just did it now because I was looking at it.
Okay, so, oh, you just figured it out just now? All right, so, okay, well, let's look at this. So the first, so what's going on here is we've got this bag full of M&Ms, and we have, we're going to take 2 M&Ms at random from the bag. All right, so we'll come back to base there in a minute. So this is homework 3.1, and so we're going to say we've got x1, say x2, and then we have x1, and so x1 is going to be the color of the first one that we select. All right, so how many colors are there? We've got brown, that's 1, yellow, red, blue, orange, and green. Brown, yellow, red, blue, orange, and green. So there's 6 different colors. We could write these out if we wanted. Brown, orange, yellow, red, blue, green. And so we have 6 different possibilities for both of these things. Brown, orange, yellow, red, blue, and green. So if I reach in, I pull out the first one and it's green. That happens right here. If it's blue, then I have, let's put it like this. Sorry, the first one is on the x-axis. So if the first one is green, I'm going to have green. And if the second one is brown, then I'm in that position. All right, and if the first one's green and the second one's orange, then I'm in that position. And if the first one's green and the second one's yellow, then I'm here. Green and red, green and blue, and then finally green and green. Okay, so there's 6 different possibilities for each of the colors, or each of the M&Ms we pull out, and so there's 36. There's brown and green in this position, and so you can fill all this in. So there's going to be 6 times 6 is just 36. So that's the sample space. If I were to go through and write all those in, I'm not going to take the time to do that, but you can see there's 6 here, and there's 6 here. So if I get green and green, that's fine. It only happens in one way. And so then you can use this idea to come up with the probabilities associated with each of these different combinations. What's the probability that both are brown? If these things are independent of each other, what we're saying is here's brown, and they're not equally likely because these proportions are different. So 12% is brown, so we'd say the probability of brown is going to be 0.12 times 0.12. That's 0.0144, so about 1.4%. And then whatever else they're asking for. So let's put in 36. 1.0144, and let's check our work. We got that right. So probability that both are green, probability that both are blue. That's the same way. Part E, what's probability the first M&M is brown and the second is green? So where's that? That's this point right here. So probability first one's brown and the second one's green. It's going to be 0.12 times, what's the probability of green? Green is 23% times 0.23. So whatever that turns out to be, plug that in here. Okay, so what is it different to get the first one brown and then the second one green? Than to get the second one brown and the first one green? Are those different events? Probabilities are the same, but the events are different, right? And if you reach in, you pull out a brown one, and then you reach in and pull out a green one, that's different than if you reach in and pull out the brown one for the green one first, and then the brown one. But the probabilities are going to be the same. So if they were to say, what's the probability that you get a brown and a green one, not in any particular order, right? What's the probability of a brown and a green? That's going to be twice the probability of the first one being brown and the second one being green. Okay, does that make sense to everybody? So it's different. If you're flipping a coin, for example, and you say, what's the probability if out of two flips of a coin, what's the probability I get at least one head? Well, I can get the head first or the head second, or I can get both heads. But it's different to get the first one as a head and the second one as a head. Okay, so let's look at number 12. A biometric security device using fingerprints erroneously refuses to admit 1 in 1,400 authorized persons from a facility containing classified information. The device will erroneously admit 1 in 1,012,000 unauthorized persons. Assume that 90% of those who seek access are authorized. So, you know, you've seen the movie. They have this secure facility. It's got very sensitive stuff in it, and Tom Cruise wants to break into this place and steal the stuff, and he's going to try and beat the system, and this is, you know, these are the odds and all this crazy stuff that they say is going to happen. If they get caught, then they're going to get I don't know, something bad happened to him. All right, so what do we have here? Erroneously refuses to admit 1 in 1,400. So how would we say this? The probability that somebody is not admitted given what? That they are authorized. All right, you're either authorized or you're not authorized, and you're either admitted or you're not admitted. All right, so AD means you're admitted. AU means that you are authorized. So we're told that 1 in 1,400 authorized persons. So given that you're authorized, the probability that you're not admitted is 1 out of 1,400. All right, that's what that says. Erroneously refuses to admit. All right, so if you're authorized, you should get in. If you're refused, then it's erroneous. The device will erroneously admit 1 in 1,012,000. So this is saying, given that you are not authorized, you're going to get in with probability 1 divided by 1,012,000. Is that right? Erroneously admit, so you're being admitted, but you're not authorized. Okay, and then here's the last vital piece of information we need. 90% of those who seek access are authorized. So let's say, what's the probability that somebody is authorized? That's going to be 90%. Okay, so imagine the scenario. The system's pretty accurate. If you're authorized, you're not going to get in 1 out of 1,400 times, which is actually probably high for something like that. I mean, imagine it's a secure NSA facility and you have 1,000 people that work there. So, you know, this is kind of like in Incredibles. If you're not authorized, or you're not admitted, the machine guns come out and they, it's like a big deal. So if there's 1,000 people going in and out, and if they're just going in once a day, they can get their lunch or whatever inside, then you would expect on average every day and a half or so to have somebody not authorized or not admitted that's authorized. So that might be high or low, I don't know. Okay, the alarm goes off and a person is refused admission. What's the probability that they are authorized? So what's going on here? We want the probability that they're authorized given that they were not admitted. The prior probability of being authorized is 90%, so anybody coming up to the door, and that's probably really a bad estimate as well, probably more like 99.999% are authorized for people trying to get in a secure location like that. But without any information, I'd say anybody walking by on the street, there's a 90% chance, or anybody walking up to the door, there's a 90% chance that they're authorized. And now we get some information. Something happens. The person's not admitted. Say, nope, sorry, you can't come in. Here's the machine guns, here's the guards, here's the dogs. We're going to look into this. And now we want to know, so what's the probability that they're authorized if they're not admitted? Okay, so how do we find that? We're going to use Bayes' theorem. And Bayes' theorem says this is just the probability that somebody is not authorized, not admitted, given that they're authorized, times the prior probability that they're authorized, divided by the probability that they're not admitted. So really what we're thinking about here is, this is conditional probability. We're saying somebody is not authorized, so that means the denominator here has to be a representation of the part of the population that's not authorized. So given that somebody's not authorized, that's going to be in the denominator. And so how do we find that probability of not being admitted? I said that wrong just a second ago. The probability of not being admitted, that can happen in two ways. They're not admitted given that they're authorized times the prior probability that they're authorized. Notice that's the same thing as what we have up here in the numerator. But there's another way to be not admitted, and that's when you're not authorized. So we have the probability of being not admitted given that you're authorized times the prior probability of being authorized plus the probability of not being admitted given that you're not authorized times the prior probability of being not authorized. So what's the probability of being not authorized? Law of complement says this is just 1 minus 0.9, so 10%. And now we can plug all this stuff in because we have probability of authorized, probability of not authorized, probability of not admitted given that you're authorized. The only thing we don't have is this one right here. How do we get that? Probability that you're not admitted given that you're not authorized. Well, it turns out that all the laws of probability that we learned about up to this point in class are true for conditional probability as long as you condition on the same thing. So if I'm conditioning on probability or the event of not being authorized, then this is just going to be 1 minus 1 over 1,012,000. Okay, so now I can plug all this information in. The probability of no admission is 1 over 1,400 times 0.9 plus 1 minus 1 over 1012000 times 0.1. So of all this, whatever that number turns out to be, and we'll plug it into Excel in just a second, of all of that probability, how much comes from that portion right there? That's all we're saying with Bayes' theorem. So let's go over here and 3.12. So we're going to say probability of not being admitted, given that you're authorized. I'm going to say the probability of not being authorized, given that you're probability of, let's put this like this, probability of being admitted, given that you're not authorized. And so then, so these numbers are given to us. This is equal to 1 divided by 1400, and this one is 1 divided by 1, 0, 1, 2, 1, 2, 3 zeros. Sure I got those right. Yeah, okay. So probability of not being admitted, given that you're not authorized, is going to be equal to 1 minus that probability. So if you're not authorized, the probability you're not going to get in is pretty high, 99.99999%. And that's probably more what these guys are worried about. That's why this number is so high. They don't, they really don't want people who are not supposed to be in there getting in. People that are supposed to be getting in, if they get denied, okay, it's no big deal. We can have the security guard come out and double check, and then they can get in. So what's the probability of being authorized? In this case, it's 0.9. It's probability of not being authorized. It's going to be 1 minus that. And so now we finally need, let's see, probability of, that we're interested in. Probability of not being admitted, put that right here. So that's going to be equal to this number times this number plus not being admitted is this times this. Of course, I messed that up. So 1 minus that. All right. So probability that somebody is not admitted, it looks like it's 10%, which seems kind of high, doesn't it? So I want to double check this. That and that. Okay, well, I think that's right then. And now the question says, what's the probability of what is it? Authorization given that somebody is not admitted? And so this is just going to be equal to this number, probability of not being admitted given that they're authorized, times the probability of being authorized, all of that divided by the probability of not being admitted. And so the probability of being authorized given that they're not admitted is very low. In other words, of this 10% of the people that are not admitted, how many of those are authorized? And it turns out that it's very small. So it's less than 6%, less than 0.6%, less than 1% anyway. And we got that right. Does this make sense intuitively?
Can you go back to the other
Here? Yeah. Does this make sense, what's going on? Imagine if you had 1 million people show up. How many of those 1 million people are authorized? Well, 900,000 of them, right? And of the 900,000 that are authorized, how many are going to be not admitted? What's 900,000 divided by 1,400? So 900,000. So 643 people are not going to get in when they should have been. They're authorized, but they're not allowed in. Okay, so of the million people who show up, how many are not authorized? Well, 10% of that, so it's 100,000. So how many of those 100,000 are not getting in? So they're not authorized, right? And the probability that they get in, or that they're not admitted, then is, so if we have 100,000, and we're going to multiply that by this number here, so we have 999,999. So basically all of them, right, are going to be not admitted. So of the total not admitted, how many are supposed to be there? Well, it should just be this number here divided by the sum of these numbers. So if we take this number and divide it by the sum of those numbers, we should have roughly the same thing. So it should be the same number, and it is. So that's one way to think about this. You've got some rare event. I talked last time about the going to the doctor's visit, right? There's a 1 in a million chance that you have some disease. There's a very high probability of detecting the disease if you have it. There's a very high probability of getting a cleared test if you don't have it. And so you'd say, well, you know, you got 1 million people taking the test. Almost all of them don't have the disease. So you're going to get mostly positive or negative test results, but you are going to get some negatives for those that do have the disease. And even if the rate is 98%, there's still 2% of 1 million that are going to get a negative test result, which is whatever that is. 1% would be, yeah. So that's one way to think about what's going on here. All right, you've got all these positives, or you got all these people that are not admitted. Some are authorized, some are not authorized. What's the ratio of those things, or what's the distribution of those things? Really, is what we're asking. Okay, so that's that one, and then let's look at number 15, and then we'll. You guys want to take a break? We've been going long enough. We need a break, or do you want to take the break at the end of class? Should we just push through and then? All right, let's just push it. All right, number 15. What happened there? Okay, a survey of 129 introductory statistics students showed the following contingency table. So people either have a Visa card or no Visa card, and they either use AT&T or something other than AT&T. All right, so we want to know what's the probability for each of these events. So what's the probability that somebody uses a Visa card, P of V? This is homework 3.15, and the first part says, what's the probability of Visa? And so we would say, how many do we have with Visa? And the answer is going to be, I'm going to sum down this row or this column. The first column, I've got 87 right here. 87 Visa card holders out of how many? 129. So this is going to be 87 divided by 129. Part A. Part B says the probability that somebody uses AT&T. So again, I'm going to sum these up. I've got 23 that are also Visa holders and 14 that are not Visa holders. So 37 total. And we've got 129. Okay, so here's where it gets a little more interesting. The probability of the intersection of A and V. What does that mean? That means somebody uses AT&T and they're a Visa card holder. So this means and. So I can come over here and look at the intersection. Visa card is this first column, and AT&T is the first row, so it's going to be 23, it looks like, out of 129. I'm going to skip part D because that's basically the same as part C. Oh no, sorry, it's not. I won't skip it. So the union says the probability of A union V. What does that mean? That means or. So in A or in V, and that happens. A is 37. All right. V, there's 87 of those. But if I add those things together, 37 plus 87, and I divide that by 129, that's not going to be the right answer. Why is that not right? Because I've counted the intersection here, this 23 has been counted 2 times. So I have to subtract that out once. So whatever that turns out to be. And then part E says the probability of A given V. So the probability that somebody uses AT&T given that they hold a Visa card. And anytime I'm conditioning, I'm changing the denominator. So instead of there being 129 participants, since I'm conditioning on V, that means I'm only in this column, and so the column total is 87. So the probability of A given V is going to be 23 divided by 87. This is the same thing as saying what's the probability of A intersect V divided by the probability of V. And we just showed a second ago that that's 23 over 129 divided by the probability of V is 87 over 129. So the 129s cancel each other out and we get the same thing. So you can think of that either way. I guess it's a little faster to do the other way, the first way. Okay, so other questions on that in the homework?
Number
17. Okay, so this one's another Bayes theorem question. Half of a set of the parts are manufactured by machine A and half by machine B. 5% of all the parts are defective. 2% of the parts manufactured on machine A are defective. Find the probability that a part was manufactured on machine A given that it was defective. So we know the prior probability of A and the prior probability of B are the same. Prior probability means without any other information, what's the probability? And it says half of the half of the parts are done on each, so that's where we get the 50%. Okay, 5% of all the parts are defective. So probability of D is equal to 5%, and 2% of the parts manufactured on machine A are defective. So given machine A, probability of defective is 2%, 0.02. So everybody with me on that? So the question is, what's the probability that a part was manufactured on machine A given that it was defective? Probability of A given defective, that's what we want to know. So we would say the probability that it was machine A, if we didn't know anything about it, is 50%. But given that it's defective, now we need to know the probability of defective given A times the prior probability of A divided by probability of defective. So this is still Bayes' theorem. It's a little bit easier because they're telling us what the value is for the defective in the denominator there. So we can just plug all this in. We get 0.02 times 0.5 divided by 0.05. So what's that, 0.2? So what does this say? Which of the machines produces more defectives, A or B? B does, right? Why is that? Well, 5% total are defective, but A only produces 2% total, or they're defective. So that means that B has to be quite a bit higher than 5% in order to pull that up. In fact, it should be 8% for B, shouldn't it? Okay, so plug those numbers in. And so what is this telling us? This says there's a 20% chance of what? That the machine A is the one that produced the part. Okay, so in other words, we took this part, we didn't know where it came from, we just found that it's defective, and now we're going to say, okay, given that it's defective, now what's the probability that it came from A? And it's 20%. So we've got information that allows us to update this prior probability. Prior probability said it was 50% because both machines are making parts. So if I were just to randomly select a part, I'd say it's 50% chance that it came from A. But now that I've got information, I can update that probability and get a better value. It turns out to be 2% or 20%. So 0.2. Okay. So other questions on the homework? Number 4. Okay, so this is a very important question. Why is it so important? Because it's on the homework? No, because it's basically the same thing as guess the secret serial number. All right, so you've got a remote control garage door that has 4 binary switches. So what does that mean? Binary means either 0 or 1. All right. The homeowner can set any code. How many separate codes can be programmed? So I have how many choices for the first place? 2. How many do I have for the second one? 2, 2, and 2. So this is 2 to the 4, which is 16, which is not very many, is it? No, that's bad. Let's check our work, make sure we did it right. And sure enough, we did. Yours probably will say, instead of 4, it will say some other number, maybe. If you try to use your door opener on 1,000 other garages, how many would you expect to succeed? Okay, so if you have 1,000 garages and there's only 16 different codes, how many times are you on average going to repeat one of the codes? Or how many duplicates are there going to be? That's what it's asking. So it should be, so this is A, B should be 1,000 divided by 16. So it's like 60 or something like that. 62 and a half. Oh. And I didn't read the rounding instructions, so let's try 63. Okay. So yeah, make sure you have more than four binary switches when you do something like that, when you guys are manufacturing. This is actually not that different from the birthday problem. If you wanted to say what's the probability of you know, obviously if you had 1,000 garages, you're going to have repeats, but if you had 5 garages, you'd say what's the probability of no duplicates, or the probability that there is a duplicate. So it's 1 minus probability there is no duplicate. This is actually very similar to the question of you know, everybody has a debit card with a 4-digit PIN. So do you think your PIN is unique? Well, as soon as you find 1,000 people, you know it's not, or whatever that is, 10,000 people, you know it's not going to be unique. It turns out that that's exactly the same question as the birthday problem. So think about that. But I think I told you guys last time that this is important, right? 2 to the 4. That's an important thing to have memorized. I want to ask you guys a question using, well, let's see, what do I want to do here? Okay, change the plan. Let's just talk briefly about discrete random variables. Discrete random variables are random variables that take on a countable number of possible outcomes. The ones in this textbook that or in this course that we're dealing with are going to be the binomial, the Poisson, and the hypergeometric. We have kind of also alluded to the uniform. And so in order for us to have a discrete random variable, we say these are the things that have what's called a countable support, or the values the random variable can take on are countable. So what's an example of a binomial random variable? If you're shooting free throws and you have somebody who makes on average 70% of their free throws, then you could say if they shoot 10 free throws, what's the probability that they make 6 out of 10 free throws? So if X is binomial, and you're going to shoot 10 free throws and the probability of success is 70%, there are assumptions that underlie this, and I'll refer you back to the videos for that. But basically, the most important one is probably independence. What happens on one trial doesn't affect what happens on other trials, and that's probably not a good assumption to make with shooting free throws. If you've ever heard of a guy named Jeff Hornacek, he's played professional basketball back in the 80s or the 90s, I guess, and he set, at the time, it's probably been broken now, but he set the NBA record for the most free throws in a row, and it was 18. And you know, they interviewed him after, and he said, you know, the basket just kept getting bigger and bigger. His level of confidence went up, and it's like everything I threw up, it just went in. And at about that same time, I heard somebody who told me this story said, when I was in high school, this person, when they were in high school, set the record for the most missed free throws in a game in his high school, in his state. And it was the same number, 18. And he said exactly the opposite. Every time I shot, the basket got smaller and smaller and smaller, and I couldn't get anything in. So binomial is probably not the best random variable for that, and there's lots of other scenarios that are not it's not conducive for, but it's used nonetheless. And so if I wanted to say what's the probability that x is equal to some little value of x, then we have n choose x. This is just a formula you can memorize, or go back and look at the videos for more explanation about this. Times pi to the x times 1 minus pi to the n minus x. Okay, so if I want to know the probability that out of 10 free throws, 6 are made, it's going to be 10 choose 6. This is the same combinations that we talked about earlier today, times 0.7 to the 6th power times we'll write it out, 1 minus 0.7 to the 10 minus 6. So that's going to be 10 choose 6, 0.7 to the 6, 0.3 to the 4th power. In other words, if you make 6, how many do you miss? You miss 4. What's the probability of missing one? It's 1 minus probability of making. So if you make 6, it's 0.7 to the 6th power. You miss 4, it's 0.3 to the 4th power. And now, do we care about the order? The answer is no, we don't care about the order. We're just saying how many, what's the probability of getting 6? So how many ways can you get 6 successes and 4 failures? Well, it turns out it's 10 choose 6, which is a big number. How do you do this with your calculator? If you've got a TI-85, probably this function's built in. If you don't, you're going to have to find combinations. What are you going to do on the exam in 2 weeks from today? Well, you're going to have Excel available to you on the exam. I think I told you guys that last week. I have confirmed it. We are going to use Excel. So you want to make sure you know how to do this in Excel. And the reason for that is because if you do it just on your calculator, what happens if you make a mistake? You got to do the whole thing over again. If you do it on Excel and you make a mistake, you can say, oh, I made a mistake. Where's the mistake? There's the mistake. You just change the one little piece, and then it calculates out correctly. So how do we do this in Excel? So I'm going to first of all say what's n, what's pi, and then in this case we have 10. Pi is going to be 0.7, and we'll say here's x is 6, and so now I want probability that x is equal to x, and so this is going to be equal to, the formula is binom.dist, binom.dist, the number of successes, that's x, number of trials, that's n, probability of success, that's 0.7. And then finally, this last one is very important. Do I want it to be cumulative or not cumulative? If I want cumulative, I put in a 1. If I want not cumulative, I put in a 0. In this case, if I'm saying probability x is equal to 6, that means non-cumulative. So there's a 20% probability, or 20% chance that whoever this person is makes 6 out of 10.
What's the Excel formula for this again?
It's binom.dist. Okay, again, you can find the similar formula for binomial on your TI-80 whatever. It's probably like binom PDF, something like that. If I want to find the probability that x is less than or equal to x, I'm going to do exactly the same thing. binom.dist x is 6, n is 10, pi is 0.7, and then I want it to be cumulative, so I'm going to put in a 1 there. Okay, so this cumulative, non-cumulative is just the difference between probability x is equal to or probability x is less than or equal to. Cumulative means we're adding up as we go, so push enter and you see that the probability that they're going to make at most 6 free throws is 35%. That means 6 or less. Okay, this notion of cumulative probabilities is absolutely essential. You've got to make sure that you know how to do this. So cumulative probability just says what's the probability x is less than or equal to. When I write big X, I mean the random variable. When I write little x, I mean any particular value. So think of it as just a variable that's not random. You can put in whatever you want there, and this is going to be the probability that x is equal to 0, at least for the binomial. Probability x is equal to 1. All the way up. Okay, again, I can't overemphasize how important this cumulative probability notion is. That's going to form the basis of everything we do pretty much from here on out in this course, especially when you get to Chapter 7, which is continuous random variables, and then applications of that and the inference that we're going to be doing. Okay, so questions about that? There are a couple other random variables. Poisson says how many occurrences do I have of a rare event? So for example, if you're talking about subscriptions to your YouTube channel, anybody have a YouTube channel? No? Well, okay, so if you want to subscribe to a YouTube channel, or if you have one or you know somebody who has one, they're interested in subscriptions. Right? They want people to subscribe. They say every video they make, subscribe, blah, blah, blah. If you know the rate at which you get subscriptions, then you can measure the probability that you get a certain number of subscriptions. So the Poisson says probability that x is equal to x is going to be e to the minus lambda to the x divided by x factorial, and this is for x equals 0, 1, 2, all the way up to infinity. So lambda tells you the average, so maybe you get 50 subscriptions per week. I don't know if that's big or not, but if you're getting 50 per week, you could say, what's the probability that in the next day you get more than 4 subscriptions in a day. So this lambda can be scaled up and down. So if I'm talking about 50 subscriptions per week, how many subscriptions is that in a day? Well, 50 divided by 7 is like 8 or something like that. A little over 7. And so then you could use this formula here, the Poisson formula, to do exactly the same thing we did with the binomial. You can plug the numbers in. To be greater than or equal to 4, since this goes all the way to infinity, you want to go use the complement rule, which says this is the same as 1 minus probability that x is less than or equal to 3. and this is, that's cumulative probability. So again, the cumulative probability shows up, and you can use that to make life simpler. Okay, so then the other distribution is the hypergeometric, and I know there's definitely a homework problem on that. The hypergeometric says if you have a bowl full of candy and you say some of these are X's and some of these are O's, and you reach into the bowl and you pull out a handful, and you want to know what's the probability that you get a certain number of successes. So if X is a success, and you know, maybe it's chocolate or not chocolate or whatever it is that you want to define as a success, you could say what's the probability out of the sample that you get a certain number of successes. So this is going to be, if we say there are capital N in the population, and we say there are R successes in the population, and we take little n as the sample size, then X is the number of successes in the sample. And so you would say, if I have R to choose from, how many ways can I choose X of the successes? It's going to be R choose X. And then you would say, of the failures, which is going to be capital N minus R in number, how many ways can I choose little n minus X of those? And then I say, that's just going to be a big number. I need to divide it by something to get a probability. How many ways can I choose lowercase n out of capital N? This is what's used to calculate things like the probabilities with when it comes to poker hands. If you ever play poker, you know the probability of getting a full house or whatever hand is you're interested in. That's based on this hypergeometric distribution. So it's not always as straightforward as this. Sometimes it's a little bit more involved. So questions. You guys have any questions for me? Okay, we'll see you next week then.